Cons- Hell yeah, I love that for us. Um, Let me just, where's the freaking record on this computer? Okay. And I'll wait for it to show up there. Uh, should we expect the slides to show up there yet? I mean, no one told me to connect to anything, so.
Yes, yes, please.
Yeah, it's
really warm.
it's like an air fryer.
Yeah.
HDMI port, do you have a?
Oh, yeah, I know how to.
Do you have USB-C? Because that's what I have.
There's no HDMI.
No.
It's a different model than mine. Oh, there's HDMI on this side.
Oh, okay, we're good. All right, let me scoot over here.
I have the same laptop.
Here, I got you. I got you. Guys, this gonna. Yes, there we go. All right, finally.
I'll put it out. I put it on that there, so.
Thank you. Thank you, King. Yes, better? No, it's not you. I think it's Zoom, right? One sec. Let me try sharing the other screen. The one that is like that one. Now good? Okay, we're all perfect. All right, we ready to roll? Awesome. There's seats in the front if you guys want. These people come in. Cool. All right, chairs. All right. Thanks for coming to the AWS workshop for iQuHACK 2024, everybody. First off, big shout out to the volunteers for bearing with us with some AV stuff and helping us get set up. So my name's Catherine Hyatt. I'm a research scientist on the Amazon Braket team. I'm one of the AWS volunteers supporting our challenge and our presence at iQuHACK this year. Our other volunteer who's going to be present throughout the weekend is Daniela, who's a product manager on the Braket team. So if you see us around, feel free to say hi or ask questions about anything. So today's workshop is going to be sort of an introduction to what Amazon Braket is and how to use it, along with some hints of how to use it most effectively for the challenge throughout the hackathon. And I'll also sort of swap back and forth to show how you can use it specifically with QBraid, which is the platform you'll be accessing Braket with through the entire event. So first, quick show of hands, who here has ever heard of Amazon Braket before? Few people. Who here has actually used it? Anyone? Okay, perfect. So our pitch was that this would be like an accessible intro for various folks. So hopefully at the end, you'll be feeling confident to start doing the hackathon challenges tomorrow morning. So it's also good that there are folks here who haven't heard of Braket before, because then I cannot waste time introducing it. So the goal of Amazon Braket is that we're providing a service as part of the whole AWS suite of services that allows you to access quantum computers. So you can build quantum circuits, quantum variational algorithms, test them with simulators or on real devices, and then run them and analyze your results. And so we provide a bunch of different tools to allow you to do this, and I'll go through these in depth and also discuss specifically how they're going to apply to our challenge this weekend, and just in general, what you'll be able to do with them over the hackathon. So quick description of what this actually is. So Amazon Braket is a service that lives in the AWS cloud. You interact with it through a variety of means, managed notebooks, which we'll talk about in a second, and I'll show you as a demo. You can also interact with it through the local version of the SDK. So for example, from your laptop or like a compute cluster you're running from, or the console that lives on the AWS website. Through all those, you talk to the Amazon Web Services cloud, which dispatches whatever it is you want to do, either to our simulators that are hosted in the cloud or to the actual quantum hardware. And there's a bunch of other services this integrates with that are all listed with their attractive icons there on the right side of the image. So this is a quantum hackathon. So it's good that we have a bunch of quantum devices available for you folks to run on. So on the service, we have right now 4 quantum hardware providers that are accessible through Braket. They're IonQ, Rigetti, Oxford Quantum Circuits, and iQuHACK. IonQ and iQuHACK are the ones that are going to be available during the hackathon this weekend, which is why they're highlighted in orange. But Rigetti and OQC also have devices that you're welcome to check out on the Braket console devices page if you want to learn more about how they work. And when you actually want to program one of these quantum hardware devices, you can do so with our Braket SDK. It's an open source Python library that's hosted on GitHub. Lets you do a bunch of different things that are probably pretty relevant to this whole event. Designing and building quantum circuits, submitting work to the actual device or a simulator, tracking and monitoring how it runs. And then also, if you want, you can run simulations locally on your hardware. So that could be like your laptop that you have right here, or some notebook instance that's hosted in the cloud, for example, on the qBraid platform. So if you want to install it locally, it's pretty simple. If you have a working pip, you'll need Python 3. You can just do pip install Amazon Braket SDK. And if you go to the homepage of the repo, you can see there's a bunch of documentation about how to install and use it. We also provide access through sort of third-party frameworks. The 2 main ones are PennyLane and Qiskit. If you've used either of those, you can take your workflow that you've already written in either sort of programming framework and run it on Amazon Braket devices, both the simulators and the quantum hardware. So if you're interested, and I see my text rendered poorly here on the slide for some reason, you can install a plugin that teaches Qiskit or PennyLane how to talk to Braket and just run your stuff that you already have on our devices. And then finally, if you want to learn more about how Braket works in general, we have like a free training program you can do, and you get a cool badge at the end. Everybody loves cool online only badges. So if you would like to check that out, scan this QR code, or you can check out this blog post introducing the Amazon Braket Learning Planning Digital Badge. That's what the QR code points to. So now I'll show you guys a demo of how to actually get access to Amazon Braket resources in our Jupyter notebooks with qBraid, and also show you the notebooks that'll show you how to run tasks on both our simulators and the quantum hardware. So we're now at a very dangerous moment where I have to switch the screen share source, so bear with me. Including the fact that I'm sharing to a different monitor. Is this going to show the right thing? Okay. Perfect. Awesome. Okay. It's showing up. And now I need to also share that on Zoom. Oh my goodness. I clicked the wrong button. Where is desktop 2? Okay. Hopefully that's showing up at the Zoom. All right, awesome, thanks. So if you go to the qBraid landing page, and let me move this annoying toolbar out of the way if I can. Awesome. And also this annoying toolbar. Zoom is like not cooperating with us. So if you come to the qBraid landing page, I have my account showing here. I guess you can all see my email now. Please don't send me weird emails. And if you're on the QBraid landing page, you can launch a lab. So that's a cloud hosted instance that will allow you to run the notebooks that talk to either our simulators or the QPUs. So I already have a lab that's open, so I'll just swap tabs. So if you launch a lab, it'll probably take a second because it's got to provision a free instance for you. If you already have your access code for QBraid. I already set this up, so we don't have to sit here watching the instance provision for like 5 minutes. So when the lab launches, you'll see a nice Jupyter Hub server like this open up. You can see you can start working in Python notebooks. You can open a Python console, the terminal, all the stuff that one would normally see in a Jupyter Hub notebook. And then on the left here, and actually let me crank up the file size if I can, or the font size, or perhaps not. It's not gonna let me do that, okay. So on the left here, you can see there's this folder QBraid tutorials. So when your lab launches, if you go into there, you can see there's all kinds of wonderful tutorials here that everybody's free to explore and run on the QBraid lab. But the ones we're going to focus on specifically are the top ones, Amazon Braket examples. It's very convenient that it's sorted alphabetically because Amazon starts with A. So if we go in here, we can see that there's, again, a bunch of folders. So we have our tutorials organized into sort of different classes, depending on what it is you're interested in knowing. It probably makes sense that getting started is the place to go if you've never used Braket before, because it will help you get started with the Braket service and SDK. And then we have a bunch of other tutorials you're welcome to look at. For example, if you're specifically interested in working with QAra's analog Hamiltonian simulator, you could check out the analog Hamiltonian simulator tutorials that have stuff that's very specific to the QAra device Aquila. Or if you're interested in running variational quantum algorithms, we have a whole folder for that. Or if you're, for example, interested in working with PennyLane. But for now, we'll just check out getting started. So there's 5 notebooks in here, and I'll just sort of move this to the side to show the titles. So these, you're welcome to go through at your leisure and check out to kind of learn how the Braket works. I'll show probably the 2 that are most interesting to us right now, running on simulators and then running on quantum devices. And let me move my sidebar over. Okay. So this tutorial running on simulators shows you how to get started with the simulators that execute locally in the notebook instance you've provisioned using QBraid. And again, I'm sorry that my font size is really small. And one thing to note about using QBraid is that in general, when you're using Jupyter Lab, you have a kernel that controls sort of which Python executable and with which settings is executing the notebook. And so if you're only running on simulators, this Python default up on the right here is perfect to use. And as we'll see in the QPU specific notebook, you may want to pick a different kernel if you want to run on an actual kernel device. But for now, we can just get started with the simulator example. So we just import the Braket SDK as sort of the top level Braket Python package. And then we have submodules for building circuits, interacting with devices, and talking to AWS on-demand devices. And in this example, we go through and prepare a GHZ state. So for those of you who might be like new to quantum computing, this is effectively a generalization of a Bell state where now we create a state that is a equal superposition of all zeros and all ones. And it's pretty nice in Braket. We just create a circuit object, attach some gates to it, and we can tell, for example, if we're using a controlled gate like C0, you can tell Braket, hey, the control is this, the target's this. Everything you would expect from a circuit builder. You can also, if you would like, make some attractive ASCII art of your circuit. This is also usually helpful to do to make sure you generated the circuit you expected. And now you're able to run on the local simulator. So this is a simulator that lives in the whatever instance you're running this on. So for example, if you're running this on your laptop, it would be executing on your laptop. Or if you're using the cloud, it would be executing in whatever instance is backing the notebook here. So for example, if your laptop does not have a lot of memory, that'll restrict the size of circuit you can simulate using the local simulator. So just keep that in mind. But because it's installed and running locally, it's completely free to use, and it's a great way to test and debug stuff before you try and run it on something that either has a long queue time or would be more expensive to use. So in this example, we just run 1,000 shots, so 1,000 executions of this circuit, and we look at the histogram of the results. It's what we expected, bunch of zeros, bunch of ones, 50-50. And you can do more complicated results. So for example, measuring expectation values, amplitudes, variances, depending on the number of shots you want to run. And then we also have some on-demand simulators. So these simulators are hosted on AWS infrastructure, and they're effectively just another device like a QHP that you can submit to. These are good to use for larger circuits, so like larger than about 20 qubits, if you're interested in simulating something like that. And the same syntax for building the circuit to submit to them applies. You just use a different constructor to build the device. So each on-demand device, whether a simulator or a quantum processing unit, has what we call like an ARN, so effectively a name tag associated with it. So if you say, I want to use the AWS device associated with this name tag, then Braket will submit whatever circuit you want to run with whatever shots or other parameters you want to use to that device. So our on-demand simulators are region agnostic. They can run in any region. Some of the QPUs are not region agnostic. For example, QRAR is only available in what we call US East 1. So you may see some of these name tags include a location like that. It just tells you sort of where the QPU is living. And I think INQ is also in US East 1, right? Yeah. So they're both in US East 1, which is great because that's the default region that we'll be in since we're in the east of the US. But if you were running on a QPU, for example, like Oxford's that's hosted in London, you might expect to see some larger latency when you talk to it. So just keep things like that in mind when you're actually submitting to something that's hosted in the cloud. It's not surprising if you encounter some latency when you do it. And when you're using the quantum devices through QBraid, so all of the participants are going to, I believe, get a specific key to use this. So you shouldn't have to worry about it specifically asking for credits. But just keep in mind that when you're using one of these QPUs, you are going to be using credits. So we do provide some tooling I'll talk about later, just to make sure that you're doing so in a way that you can track and make sure you don't, burn through all your credits early doing debugging that you could have done with the simulator. So this notebook, the running quantum circuits and getting started, shows you how to, for example, query the device properties. So see what gates it supports. You can even query the topology to understand like the layout of the qubits on the device. This is something that might be interesting for you for our challenge, which we'll talk about more tomorrow. And again, we just go through showing how you can build a circuit and run it on quantum hardware. So here we can see, again, one of these sort of quantum device name tags or ARNs that now contains a region. So Rigetti's quantum computers are on the West Coast, and they have a tag that explains this. And so, for example, if you wanted to run on one of IonQ's devices, ARIA is not currently available, but you will be able to run on Harmony. You would pass the appropriate name tag for that IonQ device, where instead of ARIA 2, this would say Harmony at the end of the string. And that will allow you to submit and run your tasks on IonQ's device using this notebook that's hosted in the QBraid cloud. And then similarly, this is how this would work for OQC's Lucy device, which is in Europe. And one thing that's quite nice is since the QPU is not available all the time and it can only execute one task at once, you can end up having quite a long queue of executions that build up. So you can, when you've launched a task, ask Braket to fetch the task back for you using the name tag that the task itself gets. And this section of the notebook shows you how to do that. That's great, for example, like if you've submitted some tasks and you're waiting for them to return, but then your Wi-Fi cuts out, something that has never happened in this data center before. Then using this functionality, you won't lose all your work. You can just recover the task by checking their ARNs or name tags. And that's something you'd also be able to see in the Amazon Braket console. Okay. And we can see indeed that if you run on one of these QHPs, you see that actually the data is not so perfect anymore because the QHP device is subject to noise. And let's see again if I can include the very risky switching of my screen. Yes, beautiful. Of course, it doesn't want to let me share the thing I want to share. Zoom. Okay. Okay. Well, you'll get a sneak preview of the rest of my slides, I suppose. I guess it would be interesting to have a betting pool at the end of this hackathon, which will happen first. I will successfully share a screen on a Zoom call from a projector, or we'll invent fault-tolerant quantum computers. Place your bets, and I guess whoever is right in like however many years that takes, I will owe you a copy. So now we're going to talk specifically about noise in quantum computing. Sneak peek, this is going to be relevant for the AWS challenge. We'll announce at 10 a.m. tomorrow. So for those of you who maybe have a lot of expertise in quantum computing, you know that noise is a factor that affects these devices. So we have some circuit that we want to run on whatever quantum hardware it is, but this circuit is affected by errors. And specifically, there's lots of quantum effects that are occurring on the device that make the results of our circuit perhaps not exactly what we expected. There's various kinds of noise that we'll discuss, and effectively, we have to find a way to account for this to make sure that we get the best use out of the device. So if you try and run a circuit on a noisy quantum computer that's larger than like some depth, you'll just get effectively like random noise out of it. Now, maybe that's great if you want to generate a lot of random numbers. I mean, generating random numbers is great. It's like a very common problem in cryptography. But if you want to get useful information besides random numbers out of the quantum computer, you have to find a way to account for and mitigate or suppress the effects of noise, which usually means understanding, first of all, what noise there even is before you can correct for it. Generally, if you want to solve a problem, it's best to know what the problem you have is first. Not always, but usually. And the reason this is such a problem specifically for quantum computers is that the devices we have are not as, let's say, robust or reliable as classical digital computers we use today. So RAM or like classical GPUs that you have in a computer also have error correcting built into them. But the error rate on these devices is generally substantially lower than on a quantum computer, which means that the error correcting codes that they've implemented are much more effective at suppressing it. But in a quantum computer, the entire system is governed by a giant quantum mechanical interaction that makes it very hard to suppress the effects of noise while still being able to manipulate the quantum phenomena that allow you to do useful computation. And what we're interested in finding out is, can we find a more effective means of doing this, both to like lower the time it will take us to have a useful application of quantum computers, and then also to better understand the noise that affects the devices we have so that we can design better ones. Cool. So as I mentioned earlier, in the Braket SDK, one model we can look at is this kind of circuit model, right? Where we're running like a series of what we have abstracted as gates on the quantum device. And there's lots of different gates that are supported in Braket. You can check out in the notebooks that I've shown. So this is kind of an idealized picture of what the quantum device is actually doing. But in the real world, there's noise that's affecting that circuit. And so to actually simulate what it's doing, we need to move away from a very simple sort of like vectorized or pure quantum state description and to a density matrix formalism that allows us to incorporate the effect of noise on the system in order to simulate it and understand what it's doing. And so to our initial idealized gate formalism, we now add what we would call like a noise channel. So this channel can affect a specific class of gates. It can affect a specific subset of qubits. It can affect specific operations like initializing the state or reading out the state at the end. And by combining all of this, we can generate what we call like a noise model of the device and use that to understand what our circuit is actually going to do when we run it on the device. And so one way of describing this noise is with what we call a Krauss representation, where we can write down the noise channel as a sum of what are called Krauss matrices. And if you don't already know what this is, that's completely fine. We have a nice notebook that I'll show in a second, explaining where these come from, how to build your own, and how to understand them. And so we combine these Krauss matrices with our density matrix representation to simulate the effect of noise on a specific circuit. Ooh, sorry, it's very dry in here. And I feel like the air conditioning not kick in. It was a bad idea to wear my warm turtleneck. So, okay, you want to use a density matrix formalism to simulate the effect of noise, just like I said, but how do you actually do that with Braket? So we have a suite of different simulators that you can use. Should remove that note. And they're sort of all tailored for doing different things, but the ones that are probably most interesting for you, if you're interested in looking at noise, are the local and then on-demand density matrix-based noise simulators. That was a lot of words, but we have a local simulator that's density matrix-based, and then an on-demand hosted in the cloud one that we call DM1. And so these accept exactly the same inputs, a list of gates and noise operations or noise channels. The difference is that DM1 is optimized for larger circuits. So in general, you should try and run anything like under about 10 or 12 qubits locally. And then anything larger than that, you'll probably need the on-demand hosted simulator for it to finish in a reasonable time or to not your laptop. But it's good to get started with the local simulator to sort of test out kind of your assumptions and see if even for small circuits, you're able to model what the QPU is doing effectively, and then move on to the on-demand one when you need to simulate larger qubit counts. So as we mentioned, this local simulator is hosted wherever you're running it. It's completely free to use and can be run at any time. And it's really good for fast prototyping, and you can build up a set of specific gates and then run a certain number of shots with noise channels, or even you can run what would be like an exact simulation to see if you ran an infinite number of shots, what the probability distribution of the outcomes should be. And you can instantiate this. Again, I'm sorry about my font size. With the local simulator we showed before, you just pass it a specific string that says, hey, I want to use the density matrix simulator. And then you're able to do so. And that'll run either on the instance that's supported in the cloud or on your local laptop. And then we have this on-demand hosted simulator, DM1, that simulates the full density matrix of the system. And again, this is probably better if the circuit you're trying to simulate is like, 10 or 12 qubits or more. Keep again in mind that just like a state vector simulation, the density matrix simulator scales as 2 to the 2n, where n is the number of qubits. So every qubit you add dramatically increases the complexity of the simulation. So it's often worth it to start small and gradually increase the complexity until you're kind of really at the edge of what you're able to do, either locally or then with the on-demand simulator, rather than going to the largest qubit count you can think of initially. So we offer a bunch of predefined noise channels, and I definitely recommend checking out our notebook about noise simulation to understand what all of these do if you're not already familiar with these kinds of errors. So these are pre-built noise channels, just like our pre-built gates, that help you simulate common sources of noise in real QPUs. So not every QPU is equally affected by all of these. And in fact, figuring out which sort of combination of these and in what ratios affect the QPU is a pretty complicated problem that might be relevant to our challenge tomorrow. So definitely encourage everybody, if you have never heard of like amplitude damping, to either check out our notebook or any of the other resources that are going to be available during the hackathon to kind of learn more about that. And then we also provide the ability for you to bring your own noise, as it were. So of course, if you want to bring your own noise music, that's great, but you can also bring your own noise simulation. Danielle is not a fan of noise music. You can bring your own noise simulation if you think that perhaps like the predefined one we offer aren't sufficient for your needs, or you just want to test something out that doesn't really fit into the paradigm that we have. So in this notebook, and I'll show you how to find that in a second, in the Cube console, simulating noise on Amazon Braket, we show you how you can define your own Krauss operators to define any noise channel you can think of, and you can kind of build those together into a large noise model of your circuit. And you can combine these together with things like initialization and readout noise to build a very sophisticated model of what the device is going to do. And this lets you run a lot of simulations while you're waiting for the QPU to become available, which is generally a more efficient use of your time than just sort of sitting there waiting for the QPU in the first place. So we let you either apply noise operations behind specific gates in the circuit, or you can say every single CNOT in my circuit should be affected by this type of noise. And every single, let's say, X gate should be affected by this other noise. And I think all of my qubit readouts are affected by this other kind of noise, or maybe only some qubits. So you really have a lot of flexibility to build a noise model that is able to reflect what the device is actually doing under the hood, and to kind of plug and play and remove things as you go. So okay. Another risky share. Let's see if I can do this. So if we go back to Amazon Braket examples and we check out Braket features, many of these notebook names are unfortunately like a little bit long, which I'm sorry for. If you check out this simulating noise on Amazon Braket, someday this will load. Awesome. You can tell this notebook has a lot of content because we have a table of it. So there's a lot of material in here about how you can first understand the density matrix formalism, which isn't the only formalism for simulating noise, and also explains the quantum channel or cross formulation for people who aren't familiar with it. We show you how to import the various things you'll need from Braket to build your own noise model. So in addition to our regular circuit observables and gates, we're going to import the noise class that lets us pull in all of the various predefined noise operators or build your own. And then, oh, this doesn't want to close. We're able to get started with the local density matrix simulator and start building a circuit where we have some gates, we add some noise to some of them, and we can control the probability of that noise affecting certain gates. So this is kind of a small example, but based on this, you can build very complex simulations of what you think the device will do. And then you're able to run the circuit using the local density matrix simulator, and you can get various results. So it could be like, these are the bit strings I measured in whatever amounts I measured them in, or you can ask for the expectation value of some observable or its variance or whatever it is you think will be most useful to try and understand what the device is doing. So again, we can define some GHZ circuit and then apply a new noise to either all the gates, which is what's being done in this case, or if we wanted a subset of the gates and run it on the on-demand simulator. In this case, we're running something on the on-demand simulator that's perhaps not the most appropriate because we're running with a very small number of qubits. But in general, you want to reserve this for when you're running something pretty big. And then we see at the end, again, a bunch of measurement counts. And you can learn how to define your own noise channels. We have a nice description of what all the predefined noise channels we provide are in terms of the cross representation, which underlies our whole noise simulation approach. So, if at the end of the day, you're really confused about amplitude dampening is, it's often worth it to just build the cross matrices and look at them and say like, oh, okay, I see how this is going to affect the density matrix based on this sort of generic formalism of these matrices. Since this is a tutorial, we don't have a huge amount of time to go super in depth into each one of these. But if you check out this notebook, it'll give you a nice introduction to how this whole situation works. We also show you how to define your own custom noise channels. As shown here, you can build some unitary matrix and build some cross operators out of it. And finally, add some noise to circuits. So just like you sort of chain apply gates, as we've shown here, you can chain apply noise to certain qubits with certain probabilities after specific gates. You can print your circuit again and see that there's some depolarizing noise and dephasing noise where you would expect. And you can also apply sort of a generic recipe for building noise into the circuit if you want to. And you have a lot of sort of knobs you can tune for how you do this. You can say, as I mentioned before, these are the target gates that this specific noise applies to. Or if you have like arbitrary unitary you're passing to the simulator, you could say, only this unitary is affected by this specific kind of noise, or only these qubits are affected by this kind of noise. This is something that you might, for example, be interested in combining with the topology of the device, which you can check using its properties, as is shown in one of the earlier Getting Started notebooks. And again, you can see when you apply this sort of model to the circuit, the noise will be inserted in the right spot. And trying to make sure that I have not left out anything else. And then, yeah, you can also apply sort of both these methods together. You can apply noise at a specific point in the circuit to a specific qubit and combine that with sort of a generic application of noise to all gates of a certain type. When you do this, just make sure you don't kind of double apply. So if you only mean, in one case, like to have a bit flip on this X, and then you apply another global bit flip, just be careful that you're not applying one extra. It's a common pitfall that I myself have run into many times when I'm building these noise simulations. And then finally, you're able to run these on the simulators. So these noise models, of course, can only be run on simulators because this kind of paradigm doesn't really make sense when you're running on a QPU. For the QPU, you would only have access to the gates. So this is a sort of simulator-only paradigm, but it lets you build up a more representative picture of what you think the device is actually doing, which will hopefully allow you to find a way to work around the unfortunate fact that the devices we have currently are noisy. And then okay, another extremely risky swap back to my PowerPoint. Okay. And the last feature we want to show off for you folks is the ability to run variational algorithms with a feature we call hybrid jobs. So hybrid jobs are designed for situations when you have some sort of long-running algorithm that generates a lot of quantum tasks and then takes the results of them, does some classical processing, and then runs some more quantum tasks. So if you're familiar with machine learning, this might be pretty familiar. Effectively, in a hybrid job, the QPU plays the role that the GPU does in a machine learning training algorithm. That's like a very sort of 30,000-foot high-level analogy. But what this allows you to do is fire and forget some long, for example, training algorithm to learn a noise model that you can run this overnight or while you go and get some coffee, and it will submit all the tasks for you, gather the results, give you lots of tracking information. And crucially, when you run on a quantum device, it'll give you priority access while the job is running. So when your job starts, only your tasks get to run. Nobody else can sort of cut in front of you, which also helps account for the fact that not only are the devices we have noisy, but the noise they experience changes over time, which is very frustrating. It's not just that they experience noise, but that the noise model is actually changing in real time. And so having priority access to the device that lets your tasks execute kind of all in one flow means that you're less affected by the drift of the device because your tasks are running with a shorter time in between. And so this kind of generalizes, like if another higher level of abstraction from just a single shot to a task, which is one run consisting of many shot executions, and then a job is a run of many tasks, each of which consists of many shots. So we definitely encourage you, if you are running something that sounds like it fits this bill, to use hybrid jobs for it. It will allow you to kind of keep track of all the tasks executing in that job, and when you're ready to run on the quantum hardware, it gives you priority access, which is pretty useful. And finally, we'll end with some useful tips for using the Braket service and hopefully have some time for questions. So there's a bunch of QR codes here. I'll try to make this bigger because the text is probably gonna look really small. Oh, my computer's not want to do that. So you've probably figured out by now, because I kept hammering the point, that it's really worthwhile to use our simulators to debug your algorithm and test how it performs. Because otherwise you'll be sitting waiting in a queue for a quantum device. So the quantum devices we have, generically, there's only one of them. It can only execute one task at a time, which means if there's a bunch of people who are participating in the hackathon all trying to use the device, it very quickly builds up a large queue. So you can be sitting there waiting a while for your task to run. and not getting any useful information. Versus if you're able to use the simulator to understand what the device you think should be doing, it can at least allow you to refine your approach for the time when you're ready to actually run on the current device. And again, as we mentioned, if you're planning to run a long series of tasks, you should definitely try and use hybrid jobs to do that. Lets you fire and forget, lets you track stuff. And we also have a nice feature that we recently launched called the remote decorator that lets you take a script that you wrote like in your notebook and run it as a hybrid job with basically one quick line of code change that involves attaching a decorator to a function. If you want to learn more about that, check out this blog post with the bottom QR code. And if you're wondering about how the queue is going to affect you, we also have a feature that allows you to actually visualize your position in the queue. So you can say like, hey, Bracket, I submitted this task. Where is it in line? And then you can see like, oh, my task is number 200 in line to execute. Maybe I should do some simulations while I wait. So you only see your tasks and jobs, but it can give you some information about how long you should expect to wait for your thing to execute. And it can be really useful to understand when you can expect your thing to run. And then I guess the other thing just to mention here, of course, is as we also keep mentioning, like these QPUs are quite scarce. So do try and be judicious about when you submit tasks to them. It's not usually worth it to submit like 200 tasks right away because you'll jam up the entire queue for everybody else. And your stuff will also take a long time to run. We also have a bunch of features in Braket and in our SDK that we showcase in some of our features notebooks that allow you to track costs. So since most of you will be using credits to run on the QPUs, using the cost tracker can help you understand as you run your circuits, how many credits did I use, and thus avoid running out of credits while you're still kind of developing whatever technique it is for the challenge you want to do. And then finally, one of the devices we're going to have available for this hackathon is iQ's Harmony. So if you go to the Amazon Braket devices page, you'll see that it will look unavailable. And that's because it is to the world at large, but it's specifically available for the hackathon. But of course, we don't want to show the world that it's available, and it's only accessible to hackathon participants. So you'll see that it's not available, but in fact, it secretly is, just only for hackathon people. As a caveat, though, it's specifically going to be processing tasks very slowly. So again, be careful submitting a lot of tasks if you're not 100% sure that's what you want to do. And with that, we have like about 10 minutes for questions. I don't want to keep folks too long in case there's like pizza or something on the side. I don't know. Or, it's like, if you want to get some water, perhaps. It's very hot in here. Anyway, thank you so much for having us. Really looking forward to see what everybody does with all the challenges. And yeah, questions. And again, I'm sorry about the screen share situation. Is there a mic we should pass around, or does anybody know? Okay, you'll just have to yell really loud then. Person in front.
Sure, yeah. I was wondering, I think you mentioned this, but just to be super sure, would we be able to manage like the infrastructure we have access to through Amazon Braket or only through QBraid?
So when you're running through QBraid, for example, if you want to submit a job, you can specify when you submit it, like this is the EC2 instance I want to run on. So you can ask like, I want to like one that has more compute or less compute, and then that'll affect the amount of credits you end up using. And similarly, if you're executing through QBraid, you can pick like which simulator you would want to use. So if you pick the local one, that runs entirely on the QBraid provisioned instance, and you would not, as far as I understand, use any credits because you're not sending anything to any of the on-demand AWS hosted infrastructure. So you're able to pick specifically like which simulator I want to use, which QPU I want to send stuff to, which EC2 instance type I would like to use if I'm going to run a job. And you're able to control like the number of shots you want to run and things like that. Oh, question in the back.
Yeah. So how do we decide, how accurate are the simulators to the actual QPUs? Should we like run multiple different simulators on the same like program before sending it to a QPU to make sure that we tested anything and there's not going to be some weird bugs once we get to the real thing?
Yeah, so in the specific case that we're looking at here, where you have like a density matrix simulator, you have to bring the noise model. So the accuracy of your simulation is entirely dependent on how good your model of the device's noise is. So we don't necessarily give you a predefined noise model. You may have to try and sort of infer from what the device actually does what a reasonable noise model is. And from that information, try and come up with a circuit that maybe kind of works better given the noise that you know the device, or you have inferred that the device has. Whether that's like picking different qubits for certain gates, or maybe trying a different decomposition of a certain gate or something like that. But yeah, part of the challenge is you have a device that you can send instructions to and you get results back. And from there, can you learn about the noise that actually affects the device and encode that in these kind of cross operations? And then in turn, take that information and make your circuit better. So it's a hard problem, but
Challenges.
I mean, you'll find out at 10 a.m. tomorrow, so. I also realized I should have moved this up because the whole Zoom has just been seeing a great recording of my chin the whole time. Sorry, everybody who's watching this online. Do we have other questions? Will they?
Yeah, we're recording this and we'll post it.
Okay, cool. Yeah, so you can watch the recording. Cool, thanks. Yeah. And again, all the notebooks are available in the Cube lab, so you can check them out like now, later, 2 in the morning, whatever it is you're feeling. And so that's available 100% of the time. And you can run those on the Cube instance. Just again, be careful because some of them do involve running on some of the AWS managed stuff that could cost you credits if you're not careful. So before just going to Jupyter and being like, run all the cells, you may want to go through and comment out anything that involves like an AWS device or anything besides a local simulator before you're really ready to run there. Very desiccated. Any other questions, thoughts? Okay. Anything on the Zoom chat? I cannot see it. So,
There's actually no conference.
Oh. Is there anybody on Twitch? Oh, there's one here. Okay, perfect.
Yeah, so once you create the circuit, you have a compiler path to optimize what's happening or.
So we don't right now, like whatever circuit you write is what will be sent to the quantum hardware provider, which may then behind the scenes execute compilation passes of their own that are device specific. So for example, on some devices like superconducting devices are a good example, not all of the qubits are directly connected. So if you try and do like a 2-qubit gate between gates like those, the QHP will then decompose your 2-qubit gate into a long series of gates to sort of move the information around that it needs. And we don't control how that process occurs. So if you want to ensure that the gate or the circuit you specify is exactly what's run, we do provide a feature called verbatim that is, as the name implies, it tells the QHP like, do not compile this section. I want this run exactly as is. But the problem with that is, especially on devices where the qubits are not directly connected, it can introduce a lot more error. So if you really want to make sure that whatever it is being run the way you want, then you can use that. Another option for QPUs, you can disable qubit rewiring. So if you submit like a 5-qubit circuit to a device that has more than 5 qubits, the QHP can say like, hey, I'm going to take your circuit that was specified on qubits 1 to 5 and actually run them on qubits like 13, 26, and a long list. And you can tell them like, please don't do that. Just do exactly what I said, or I'll allow that. So it's kind of up to you to experiment with those features. Those are also documented in notebooks in our Braket features. Another very risky switch. Yes. Okay. So you can allocate qubits on various devices, and you can map your qubits around. You can look at the topologies. Using the console, you can also get information about the specific gate fidelities on devices, which you might find useful if you're trying to understand the noise that affects them.
But compilers are usually written very specific to the hardware, but qubit has supports so many different platforms. So for the challenge, can we just pick one provider?
I would wait until 10 a.m. to find that out,
Okay.
but. Sorry, I know it's a little over 12 hours away, so. But yeah, in general, not only the compiler, but the noise model is extremely device specific, so. If you have a challenge that involves noise, you probably want to focus on one device. At least that's what I would do. Cool. I saw some other people with their hand like kind of up earlier. Was that a question or just like I'm stretching? Cool. Well, if not, I guess we can end a minute or two early. Thanks, everybody. And thanks again for bearing with us with the Zoom. And if anybody wants some coffee cake or I don't know what this is, blueberry muffins, apparently, you're welcome to come have some or hang out in the hallway where it's probably 20 degrees cooler. Thanks so much. Stop sharing.